Okay, so in this problem, we've got tangents and secants, and there's actually two ways you can approach it. Since we're sort of in reduction formula mode, you might be tempted to take that route, but why don't we do it in two different ways? Let's do it the easy way, the easiest way. And over here, we'll, after we do that, we'll do it using the reduction formula stuff, which you actually don't need. But okay, the easy way, you might notice that if you sort of forget the new stuff you've learned, this is a relatively simple substitution problem. Why? Well, because notice that if you let u be tangent, the derivative of that, the derivative of tangent, is simply secant squared. And so you pretty much have du right there automatically. And this just turns into u to the fourth. So this is just equal to the integral of u to the fourth du. And this is just u to the fifth over 5 plus c, or tangent to the fifth over 5 plus c. Too easy, right? Well, okay. Let's do it slightly differently, just because sometimes you kind of need to get a little bit more messy. I'm going to rewrite it, and we're going to do it all over again. Now, this time, instead of just using substitution, let's instead let's turn this secant squared into, we know that secant squared is 1 plus tangent squared, theta. And so then this integral would be equal to the integral of tangent to the fourth, theta, times 1 plus tangent squared theta, d theta. Okay. And then if you distribute this, you would get tangent to the fourth theta plus, the integral of that, plus, why don't I break this up? I'm going to break it up into two integrals. So I'm going to do the integral of tangent to the fourth, and then plus the integral of tangent to the sixth theta, d theta. Okay, now at this point, you can either make it really complicated or pretty simple. Okay, so the complicated way would be to use the reduction formula on this one and this one. But the simpler way would be to only use the reduction formula on this one. Well, why would you do that? Well, when you use the reduction formula on this integral, your integral that's going to be left over is going to be a tangent to the fourth, right? Because you reduce the degree by 2. And so that one you're going to be able to combine with this tangent to the fourth. Isn't that great? Okay, so then I'm just going to leave this one alone for now. Now, if you were to do the reduction formula on both, then you would still get the right answer, but it would take you quite a while. Okay, so if I use the reduction formula on this one, I would get plus tangent to the fifth. Oh, sorry. Not x, theta over 5 minus the integral of tangent to the fourth theta, d theta. And what do you notice? What do you notice? What happens right there when you combine these two? Adios amigos, right? And so all you get is this function right here, tangent to the fifth theta over 5, and then plus some constant c. And notice it's exactly the same as what you got over on this side, right? And that's it. All right, now on this one, you're thinking about what to do, and so you tell yourself, well, hey, the derivative of sine is just cosine, and notice that they have the same argument. And so if you let u be sine of 2x, for example, then du would just equal to 2 cosine of 2x. And so then over here, all you have to do is put in a 2 and then a 1/2 on the outside. And so this right here is going to be your du, and then that's sine of 2x is just your u. And so then what you have is 1/2 times the integral of u du, right? And so then this is just equal to 1/2 times u squared over 2 plus c. So this is just sine squared of 2x over 4 plus c. And that's it. Okay, so in for this integral, it doesn't seem like anything too obvious right now, but you notice that dx over x, this is the same as 1 over cosine of x dx from 0 to pi over 4. And 1 over cosine, well, that's just secant of x. And remember that, so I'm not going to derive the antiderivative of secant, but remember that to find it, if you want to do it over again, you do a u substitution where you let u be secant x plus tangent x. And so if you do that, you would get natural log of the absolute value of secant x plus tangent x. So I'm not going to go over how you do that, but if you forgot, you should probably go over it at least one more time. And so this goes from 0 to pi over 4. Okay, so then what I have is natural log of the absolute value of secant of pi over 4 plus tangent of pi over 4 minus natural log of secant at 0 plus tangent at 0. Okay, so now let's try to figure out each one of these. Secant of pi over 4, well, cosine of pi over 4 is root 2 over 2, so then that means that secant is going to be 2 over root 2. Tangent of pi over 4 is 1. Secant of 0, well, cosine of 0 is 1, so secant is going to be equal to 1, and then tangent of 0 is 0. And then if you rationalize this also, this just equals to square root of 2, right? So 2 over root 2 is the same as square root of 2. So this is going to be natural log, let me pick a different color. How about purple? Natural log, absolute value of root 2 plus 1 minus natural log of 1, which is 0. So that's it.